So, chapter 9 is about chemical bonding. Okay, we're going to talk about the basics of chemical bonding and what is a bond and the bonding types. And then we're going to use this information for chapter 10 to actually answer a fundamental question of chemistry. What shape is it? Okay, so let's go ahead and start talking about bonding. So what is a chemical bond? It is a stable arrangement of atoms, and basically it's the reason that things tend to come together is the formation of a chemical bond. Okay, without chemical bonding there would be no reactions, nothing would happen. Everything would just be hanging out by itself. Now there are several different types of chemical bonds that we're going to be dealing with, and do know that there is a difference between chemical bonding and not James bonding. There is a difference between chemical bonding and a physical bonding. Okay, like glue. Okay, most glue is not actually chemically bonded. It's physically bonding two pieces together by absorbing into the material. That's why it's really hard. You can't use Elmer's glue on metal because it doesn't permeate the metal. And it's really the permeations that cause the adhesion to happen. So chemical bonding is slightly different than physical bonding. Yeah?
What about atoms?
Atoms in...
Because the definition is...
Atoms in an element. That's excellent. It's an excellent question. Believe it or not, we have a perfect answer to that. And that actually comes down to the bottom here. Okay, we'll talk about it in just a second. But we have ionic bonds. See, I told you I'd do that. Ionic bonds, which we've talked about all semester, right? It's ions. The bonding occurs between two ions. There is covalent bonding. This is when we share electrons, and that can be either polar, nonpolar, or network. Okay, and we'll talk about polar and nonpolar. And network is actually kind of a subset of both polar and nonpolar, mostly nonpolar. But a network covalent would be something like a diamond or silicon. Okay, so if you have atoms of silicon, it is all together in a network covalent bond. And then finally, metallic bonding. Now this is what tells us, since most of the periodic table is metals, this is the bonding theory that tells us why metal atoms stay together. Okay, so why two atoms in an element stick around together. Also, all of this is governed by the valence electrons. Okay, remember what are the valence electrons? The outermost electrons, the things in the highest quantum number, principal quantum number. Okay. Now, I also want to point out this guy, August Kekule. Okay. Why do I like to point out this guy? Well, he's the guy who determined the structure of benzene. But I want to point him out because he was a drug addict. So I'm going to tell the story, probably not today, but I'll tell you the story of Kekule, the opium hound. All right, so since everything's governed by the valence electrons, what we're going to do is we're going to take a look at a way to shorthand our valence electrons, which, you know, we've already shorthanded the electron configuration quite a bit. This is just another step. And this is through Lewis dot diagrams. Now, the way we draw a Lewis dot diagram is you place the element symbol, so something like hydrogen, and we place dots around the atom in order to show valence electrons. So how many electrons does hydrogen have total? One. So we put a single dot. There's hydrogen. Now it doesn't matter where it goes. No, this is the same as hydrogen up here, hydrogen over here, and hydrogen down here. But we do try to stick to top, bottom, left, right. Okay? Where do you start?
Yeah.
Doesn't matter.
In the homework, though, I was doing it in there, like, you have to start at a certain place.
That's probably homework because of the computer.
Okay.
In order to grade it, they're telling you to start in a specific spot.
Okay.
And that's why.
Okay, well, no, like, it was on that, it was a multiple choice.
I think you're supposed to start on the top, it's traditionally.
Okay.
We always
Yeah.
start on the top and go clockwise, or counterclockwise.
No, I think we go clockwise.
I always went counterclockwise.
It doesn't matter. It does not matter. If there's a question that asks about, where do you start, it does not matter. Because as you're going to see when we start drawing Lewis structures, I'm going to show you a method where it really does not matter at all, and it actually helps you if you start in different spots. Okay? Now, the thing that we do that does matter is that we're going to follow Hund's rule. Okay? Now, what was Hund's rule? Right. In other words, we're gonna half fill everything before we fully fill it. Okay. So energy is minimized when spin is maximized. Now, what does that mean? Well, if I'm gonna do, say, boron, I'm gonna have 3 dots around boron, 3 for its valence electrons. But when I go to carbon, I'm gonna have 4 dots around there. Even though, if we take a look at 1s2, 2s2, 2p2, that's its electron configuration, right? These would be unpaired, right? But these 2 electrons in the s should be paired. Well, we're going to pretend that they're not. Okay? You laugh, but there's actually a reason behind this. Lewis dot diagrams existed before the electron. So, yeah, Lewis dot structures actually come before the electron. It was nothing but a way to imagine how atoms came together in bonds. It just so happens it fits with valence electrons.
Impressive.
Well, there's a reason it fits with valence electrons. They didn't know about the electron, but they were able to use it. It's sort of that idea of you don't have to know the nature of all of the universe in order to understand that, hey, I can use parts of it. And then you dig deeper into the meaning behind it. Okay? So we just pretend it's not. And then if we go to nitrogen, then we can double them up. Okay? And move on. Now, remember that to determine the number of valence electrons, it's the group number, right? Okay? For the A's, for our main group elements. Here we have the periodic table showing the Lewis dot structures for all of the main group elements. Now, elements that are in the same family behave the same. Why? Same valence electrons. Same electron configuration. I mean, seriously. That's why. Okay? Now, there is something that is notoriously missing. Transition metals. And, yeah, my F block stuff, right? Why are they missing? They're unpredictable. That's really all it is. They're unpredictable. Because sodium forming a +1, predictable. Magnesium forming a +2, predictable. Aluminum forming a +3, predictable. Chromium, +1, +2, +3, +4, +5, +6. Unpredictable. Okay? So that's why we don't deal with the transition metals. When do you deal with the transition metals? Your last semester as a chemistry major, you take the class that deals with transition elements and you pray that you pass the class so that you can graduate. And then you go, thank you for rounding up 0.2 points to allow me to get my C, which is what I had to do. 0.2 points. Well, I rounded up. I probably shouldn't have. 0.2. 0.2 points. Everything the transition metals do is what's in that class that is so difficult. Transition metals are very difficult because those d electrons mess everything up, which is why we talk about the transition metals. We don't even get into the F block because the F block's even more screwed up. Okay? So far, so good? All right, so let's start off with the easiest bond to explain, the metallic bond. We call this the sea of electron model. Now, there's a picture there. I drew it myself, so no laughing. Thank you for the laugh right there in the middle of me saying no laughing. The white spheres are basically the metal atoms, or the nuclei. And these red spheres are supposed to be electrons, the valence electrons specifically. And they're just supposed to be all over the place. Okay, there should be a lot more of them, but I'm missing them. Okay? Because I tried to make little smaller dots and then it just looked like it had the measles. So you've got all these electrons, just this sea of electrons. You can think of it in terms of like a box. Okay? Imagine you have a box filled with oranges. Okay? And then you put packing peanuts all around the oranges. The packing peanuts are like the electrons. They're free to move around. You can shake the box and the packing peanuts are going to go wherever they're going to go. Okay? Same thing here. The atoms are held rigidly in place because it's like an electron glue. Okay? It explains conductivity. Metals conduct what? And heat. Good conductors of heat and electricity. So electricity, why is it a good conductor of electricity? Well, none of these valence electrons are actually tied to any one atom. Okay? So if you apply a force, known as the electromotive force, otherwise known as voltage, across a piece of metal, it's going to force the electrons to flow. What is the flow of electrons? Electricity. Okay? Now, how does it explain heat conductivity?
Because they're close together, so the heat would flow through them.
Right. They're close together. The atoms are close together. So, remember, heat is just molecular motion. So they're sitting there bouncing around, and since they're close together, they can bounce and hit each other even closer. Now, these metal atoms are actually packed pretty darn tightly together. Okay? Shine. Bless you. This is one of the weird ones to try to explain. But shine, if I shoot a photon of light at a piece of metal, okay, it's going to interact with the surface electrons. Now, those surface electrons basically sort of reflect the light back out at you. Hence, metals are shiny. Okay? I'm oversimplifying what happens because I don't think we have to talk about surface plasmons and all sorts of weird stuff. Electrons on the surface, boom, bounce back. All right.
How about some metal?
What about malleability and ductility? What is malleable?
That's what breaking.
You can pound it, right? It deforms when you hit it. What about ductility? What does ductility sound like?
It's like a wire, right?
Right, you can pull it into a wire, like a duct. Okay? It can be stretched out. How does this explain malleability and ductility?
It's sort of like,
How about somebody different?
is it not a rigid lattice?
It is not rigid.
When you move it, it stays, it doesn't have any spring to pull it back.
Well, but why does it stay?
Because it's not rigid in the first place, there's nothing to hold it into its original position.
Nothing to hold it in its original position. It's not rigid. But why did the atoms stay? Why don't, if you hit it, why don't they just fly off?
Because they're tightly held together.
By what? By the electrons. Those electrons that are sitting around there cause the attractive forces. Now, it's a good attractive force, but it's not anything nearly as attractive as something like a covalent bond. Whereas the network covalent bond in something like silicon. Silicon, very shiny, very, very brittle. Okay? If you hit silicon with a hammer, it will shatter because they are held rigidly in place and not allowed to move, not allowed to flow. So that also explains ductility. You pull them into a wire, the atoms tend to flow over each other, much like a pencil. When you use a pencil, what you have is sheets of graphite that are sitting on top of each other, that you're shearing off sheets of graphite and putting them onto the paper. Okay? Does that make sense? All right, so the ionic bond. Ionic bonds occur when you have a transfer of electrons from one element to another. What do we call that type of process? Redox. Redox reaction. Now, what's holding these ions together is simply positive and negative charges. Okay? The positive charge wants to be next to the negative charge. Now, the energy of that interaction can actually be calculated. That is, E electrostatic is equal to kappa Q1, Q2 over R, where the Q's are charge, R is a radius or a distance, and kappa is a constant, known as the permissivity of a vacuum. Okay? Who cares? It's a constant. Okay? Now, this electrostatic interaction is what we call the lattice energy. Okay? That's the energy holding the ions into place. Okay? Now, you're not going to have to calculate the electrostatic energy, okay, from this equation, Q1, Q2 over R. You don't need to calculate anything from that. But we're going to use that equation to actually understand relative strengths of ionic bonds.
Kappa is kappa. Because one of your charges is always going to be negative, and if you have a negative electrostatic force, wouldn't that be a repulsion instead of an attraction?
Again, don't get caught up on the signs. It doesn't really matter.
Can't there be a bunch of different values?
No.
Isn't there like isn't one of them like the Coulomb constant?
Well,
Is that a whole different thing?
it is. When you have different values, you know what the different values of a constant are?
Yes.
No. What's different values of a constant?
You can't.
Yes, you can.
Okay.
Sure. The gas constant, 0.0821 liter atmospheres per mole Kelvin, is the same as the gas constant, 8.314 joules, right, joules per mole Kelvin. It's just different units. So when you have different constants, it's the same constant, different units. No, it's okay. No, don't get hung up on the charges. You're not going to have to calculate anything. Again, with the charges on something like that, the electrostatic interaction, the charge tells you what type, whether it's attractive or repulsive. That's all it tells you. But because we're dealing with oppositely charged particles, it's always going to be an attractive. So it doesn't matter. Who cares? Okay? All right. So let's talk about the Lewis bond, Lewis dot symbols, and the ionic bond. So here we have our lithium, okay? 1s2, 2s1. It's going to lose that electron and give it to fluorine, which is missing an electron. It wants to have 8 valence electrons, right? The octet rule we had talked about. Atoms tend to gain, lose, or share electrons to gain a valency of 8. Now, afterward, what's holding these together is that lithium ion attracted to the fluoride ion. Really, what we have here, just I want to point it out, this would be the formation reaction. Okay? That's how we form lithium fluoride. Lithium plus a fluorine atom, notice fluorine atom, forms lithium fluoride. Okay? Now we can actually write this stepwise. The first step is lithium, as a metal, has to lose an electron. So, you write it as a reaction. Lithium becomes lithium cation plus an electron. Fluorine has to gain an electron. The electron plus the fluorine atom makes the fluoride ion. So, what is this first portion called? It's got a specific name. What do we call it? It's the ionization energy, right? It is an oxidation, but it's ionization energy. What would this be? Where we, right, this is the electron affinity. Should be E, little e, electron affinity. And then this would be the formation, right? Okay. This formation would correspond to the lattice energy. Okay? So, ionization energy, electron affinity, lattice energy. Sounds like we're going to talk about energy. Okay?
Is the same as the lattice energy?
The formation reaction is not the same as the lattice energy. Just give me a slide or so, and we'll see what I'm talking about. Okay?
I'm not really talking about the same thing, but when you put it down on paper.
Oh, we're talking about the same thing. It'll be okay. Yeah, just wait a slide. All right. So, lattice energy. Remember, I said we are not going to calculate. You are not going to calculate the actual energy from that equation. But what we are going to do is we're going to use our knowledge of that equation to understand who's going to be stronger than whom. Okay? So, it's directly, the energy of the electrostatic interaction is directly proportional to charge. So the higher the charge, the higher the energy of the interaction, the bigger the lattice energy. It is inversely proportional to radius or to distance. So the smaller the ions, the larger the electrostatic interaction. Okay? So what we're looking for is, if we want a really high lattice energy, we're looking for really small, really highly charged ions. Now, sometimes you can't get really small and really highly charged. Sometimes hard to do. But take a look here. We've got magnesium fluoride versus magnesium oxide. The magnesium oxide has a higher lattice energy. Why? Well, in magnesium fluoride, you've got the magnesium, which is a +2 in both cases, but you're going from a -1 to a -2. So you're increasing the charge. You're doubling the charge, right? Now, it doesn't quite double the lattice energy. It's not necessarily a 1-to-1 thing, okay? Now, for lithium fluoride and lithium chloride, what's the difference? Well, the fluoride ion is much smaller than the chloride ion. And look at the lattice energy, 1036 versus 853. So, the smaller, the more highly charged, the better off you can be, okay? So we can use this to pick between who's going to be stronger than whom. Okay? Do you want to see an example problem type? Yes. Oxygen is larger than fluorine. Right. Okay, I see the question. How are we going to determine when they're really close together? The point is I'm not going to ask you when they're really close together, okay? Because it's hard to determine. That would be a difficult thing. So a typical type problem might be something like this. That doesn't make any sense. Sodium chloride versus potassium bromide, okay? Which is going to have the higher lattice energy? Well, what do? Take a look at the charges. That's a +1, that's a -1, that's a +1, that's a -1. The charges have nothing to do with this, okay? So now we have to deal with what's the size. Potassium is bigger than sodium. Bromine is bigger than chlorine. So who's got a stronger lattice energy? Those guys that are smaller. So sodium chloride is stronger than potassium bromide. Yeah.
Would we ever run into the situation where, say, like, potassium may be bigger than sodium, let's say,
Magnesium oxide or something.
So I hold on, just I got an idea as to what you're, so something like sodium chloride versus potassium fluoride, where this one is, the sizes are really hard to differentiate. No, that's the too close thing. There's going to be a factor that tells you, hey, this is going to be the thing. So might do something like sodium chloride versus magnesium fluoride. That we could do. Why?
Fluoride is smaller than fluoride.
Fluoride is smaller, and magnesium is a +2. I mean, right there, magnesium being a +2. Boom. That's going to make it larger. Okay? Does that make sense? There will be a factor, whether it's charge or whether it's size or whether it's a combination of the two, that's going to tell you, hey, this one is going to be stronger than this one. I'm not going to give you something that might be a little wishy-washy. Okay? Doing sodium chloride versus potassium fluoride, yeah, tough call. Okay?
What's the right answer?
I'd have to look it up. In all honesty, I would have to look it up. My instinct would probably be that the potassium fluoride actually is stronger.
Fluoride is a big.
No, the reason actually comes from a different theory, what's known as hard-soft acid-base theory. Too hard and hard acid and a hard base generally are stronger together than a soft and a soft. So, yeah, it's so sodium would be well, actually, no, sodium would be a harder acid, and fluorine would be a softer or a harder base. So potassium being a softer acid, I still tend to go with the potassium fluoride. This is what I said, give me a couple of seconds for. This is the slide. This is the key. This is the Born-Haber cycle, okay? So the Born-Haber cycle is a pictorial diagram of, well, let's take a look at the bottom here. Delta H overall is delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5, which is another restating of what? Hess's law. This is simply Hess's law. We're going to take the formation of an ionic bond and break it into its component steps. The sum of the energies of those component steps must be the enthalpy of formation. See? So that's what we're talking about, is the enthalpy of formation. We're going to get that from those individual steps. Okay? So the first step here, delta H1, is lithium solid going to lithium gas. Why? What? Why, huh?
All these things deal with atoms in their gaseous state.
Right. Ionization energy is a gaseous state thing. You have to deal with it in the gaseous state. Because ionization energy has the definition of the amount of energy required to remove an electron from a gaseous atom. Okay? Now this does not mean that if I take some lithium and heat it up a little bit and stick it in fluorine gas that it won't react, that I have to have gaseous lithium. Solid lithium will react with fluorine gas. Okay? But to understand the energetics, this is our imagination of how this works. Okay? So, first we sublime the lithium, then we can ionize the lithium, and that's simply the ionization energy, the first ionization energy. Okay? Now, in our reaction for the enthalpy of formation, we have to take the material in its standard form, right? Which fluorine is not just F. It is F2. But because we have to take half of that, the first step we have to do is we have to dissociate it. So this is the energy of dissociation. This is breaking that F2 into two singular F atoms, both with 7 valence electrons. Okay? So it is what we call a homolytic bond cleavage. We break the bond homolytically, meaning it breaks the same. Okay? Once we have fluorine, then we can add an electron, which is electron affinity. Now, I'm pretty sure I said it in this class, but notice that they have negative electron affinity there, because the book, for some reason, decides that they're going to make electron affinities positive. I think it was a publisher-wide thing. When I was in school, they were negatives. They were negative values. But somehow they just turned them into positive values. I know why. I'm pretty sure I understand why. Because then you can say, oh, it follows the same trend as ionization energy. Electron affinity goes up as you go across, because you're comparing positive to positive. But remember that electron affinity, adding an electron, usually gives you energy back. It is an exothermic process. So rather than saying that ionization energy and electron affinity follow the same trend, it's better to actually say that electron affinity becomes more exothermic as you go across a period. That's really what it means. Okay? So it becomes more exothermic as you go across the period. So that's why they throw a negative sign into there when there shouldn't be a negative sign from the tabled values that the book gives. Okay? Now, if you were to just add those 4 pieces up, what you would see is a positive delta H, meaning it would be endothermic, highly endothermic, 500 kilojoules per mole. But the energy of the electrostatic interaction, that lattice energy, which again is a negative value because it's an attractive force, negative 1017 kilojoules per mole. That's a huge amount of energy you get back from the formation of the ionic bond. And hence, the overall delta H for the reaction is hugely exothermic. Lithium fluoride, very, very stable compound. Small ion, lots of lattice energy. Okay? Does this make sense? Given the information, do you think you could reproduce this sort of diagram? Or at least fill in, knowing that first thing is sublimation. So sublimation, ionization, dissociation, electron affinity. So sub, ion, dis, electron affinity, then lattice energy.
The steps were very slightly, but almost equal.
Yeah, very, very, very slightly. Because most of the time,
Your gas is a diatomic and sublime
right.
solid.
Yeah. Or if it's not a diatomic, then sometimes it's octatomic or more, or pentatonic. Yep, 5 of them. Phosphorus. Or actually tetra. Yeah, tetra. P4. Phosphorus is 4, not 5. So, okay? All right. So, covalent bonding. Covalent bonding comes from sharing of electrons. Now, this sharing can be either equal or unequal. Okay? And we'll talk about what influences those factors. What is equal versus unequal? Now, what happens is we actually, as 2 atoms come close together, their orbitals start to touch. And when they come close enough together, there's an overlap of the orbital. So it's this overlap of the orbital that allows, it's region of electron density, or where electrons can be found. So if they share the same region of where the electrons can be found, each atom feels as if it has the electron, even if it doesn't. It feels as if it does. Now, there is a specific distance at which bonding occurs. We call that the bond distance or the bond length. And the sharing can actually happen with multiple pairs of electrons. So these are all pairs that we share. If you share one pair, that's a single, two pairs, double, three pairs, triple. Okay? So 1 is a single, 2 is a double, 3 is a triple.
Which subshell of the electron is most likely share? P or
Which subshell is it most likely to share?
yeah.
That is an interesting question. The answer to which is yes. It's just going to share. Okay? We're not going to worry about what orbital we're dealing with yet. Okay? Wait till the next chapter and we'll see what actually happens. Because it's not, things can't be explained by simple orbital overlap. There's more to it than that. We're starting off simply and getting a little bit more complex. Chapter 10 carries it through a little bit more advanced. Okay? All right, so here we have bond lengths. Okay? For hydrogen, 74 picometers. First, if I take half of that, what do we call that? Somebody that I haven't heard from. I've been challenged. It's no offense to you guys. It's just I've been challenged to make sure that everybody sort of answers questions more equally.
We take half of it.
Yeah.
Do you prefer to be digital or do you prefer the units?
I'm not asking for the math. I'm asking for what does it really mean? What is half of that distance?
The radius?
The radius, the atomic radius, right. So that's the radius. Okay? Now the question is, how do we measure that distance? Is there a little dude with a ruler going, yep, 74 picometers?
No, we do it by that spring.
Right, we talked about the spring stuff. That if you hit it with light, you can change the frequency of the vibration. And by using Hooke's law, which is talking about springs, masses attached by a spring, we can actually calculate an average distance. Okay? And what we do see, though, is there is a trend. That a triple bond is going to be shorter than a double bond, which is going to be shorter than a single bond. Which makes sense. The more stuff you're sharing, the closer you want to be to it. Okay? For example, if you lend a friend $50,000, are you going to let that friend out of your sight until they pay you back?
No.
No. You're going to be really close to them. But if you lend them $5, okay, $5, maybe I'll see you, maybe I won't. Okay? A lot different. The more you share, the more pairs you're sharing, the closer the nuclei are going to get to each other, the shorter the distance, because there is more attraction for those three shared pairs. Okay? Does that make sense? So when we talk about bonding, okay, and the energetics behind it, let's draw a picture. Here we have the distance or the radius. Probably distance is a better term for this. How far apart they are from each other. We have the 0 point energy there. Now, if two atoms are infinitely far apart, then the energy of their interaction should be close to 0. In other words, they don't see each other. Now, as they get closer and closer together, there's going to be some attraction. The nuclei are going to be attracted to the other atom's electron. Okay, so they get closer and closer, and then finally, they hit a nice overlap. Okay, and that minimum is the bond length or bond distance. Now, if you get closer, if you try to push them closer, what ends up happening is the energy goes up really, really fast.
And they repel each other.
Right. So you start to get attraction between the nuclei and the electrons which starts to overwhelm the electron-electron repulsion. Okay? Then, when you get to that bonding distance, that is the perfect distance at which the one nuclei goes, okay, I got that electron, and the other nuclei goes, okay, I got that electron, and we're happy. We're balancing the repulsive forces of the nuclei and the repulsive forces of the electrons with the attractive forces of the nuclear to the electrons. Okay? Does that make sense? Now, why am I talking about this, other than the fact that you asked a really good question on it? Why am I talking about this? It's because what happens at this point. Okay? Now, if we're dealing with hydrogen, okay? So 2 hydrogen atoms. If I can mash these things close enough together such that I get past all the nuclear repulsion, I can actually fuse the nuclei into a helium nucleus, nuclear fusion. Okay? And so fusion is different than fission, right? Fission is what they do at Byron. Okay? That's when you break apart a big nucleus and turn it into smaller nuclei. Okay? Fusion is the opposite. You take 2 light nuclei and turn it into a heavier nucleus. Okay? Now, the key to why I'm talking about this is that we've never been able to get enough energy back than we put in. In other words, the amount of energy we add to get past this hurdle is always more than what we get back when they fuse. Until a couple of months ago, we are really, really close to the break-even point, the tipping point. Finally, with new advances in technology, we're getting to the point where we might make that crest. Now, why am I saying this? Because energy is a huge problem in today's society, right? $3.79 a gallon when I drove past my gas station this morning. And I remember when it was under $1 a gallon. I could put $5 in my car and drive for nearly a month. I didn't go very far, but still, $5 and drive forever. Not bad. Okay? Now, yesterday, I put $75 into my gas tank, and that's going to last me, hopefully, to the weekend. I drive a lot farther now, but the point is, it's very expensive. Energy production is also very expensive, no matter what form of energy you are dealing with. Okay? But with fusion, the amount of energy that you get back from fusing should, hopefully, lower energy costs a lot. Should. Yeah.
Did they ever touch on what would do with that mixture? Or what would we do after it was fused?
But the thing is, it's helium.
Well, it's helium.
It's not radioactive.
Yeah.
But
Fill up party balloons. That's what I would do.
would it be possible that we could have a cycle between fusion and fission?
Well, you can eventually, with more energy, you can fuse larger nuclei.
Right. So
Less and less
we could continue to try to fuse them, but it's more and more energy. It's not that it's less stable, it's more and more energy. Because fusing, believe it or not, is actually not that tough to do if you have the right conditions, such as a lot of mass in a small amount of area, known as the sun. Okay? And it fuses all the way up until iron. So iron, pretty big, pretty stable. Okay? But helium, the only place that we find helium on Earth is from uranium radioactive decay. So all of the helium we have on Earth has to have come from uranium breaking down, which is kind of sad if you think about it, that we use the decay products of uranium to fill party balloons, or to make ourselves sound like Mickey Mouse, right?
Helium gonna be rare,
Helium already is rare.
like escaping the atmosphere.
All right, so covalent bonding. Why do atoms share electrons? It's because they want to have a full valence shell, the octet rule, okay? And the sharing of electrons is more energetically favorable, especially when we hit our nonmetals. Because the nonmetals have a really high electron affinity and a really high, bless you, a really high ionization energy, which means they're not going to give away an electron, but they really want to take an electron. So there's the only one compromise, and that's to share the electrons, okay? Especially take a look at fluorine. I mean, fluorine is just the ultimate wanting to take away everything, okay? So when we share these, there's a couple of different ways we can draw these. You can draw it as like a Venn diagram, like that, which nobody does, okay? It's probably the most common is to have the dash, which represents a shared pair of electrons. Now notice all these lone pairs that are sitting around the outside. Those lone pairs must be present. If you do not put those lone pairs there, you do not have a correct Lewis structure. Okay? So they must show up. Okay? Does this make sense? All right, so the sharing of these electrons, as I said, can be equal or unequal, or nearly equal. Okay? And if we have an equal sharing, what we have is a nonpolar covalent bond. If we have an unequal sharing, that is a polar covalent bond. Okay? And the way we determine this is through electronegativity. Remember, what is electronegativity?
Likeliness of a pull two shared electrons towards itself.
Right, the tendency of an atom to pull shared pairs of electrons toward itself. Okay? Now, the differences in electronegativity values help to determine the polarity. Now, your book, like many books, takes kind of a really simplistic view of it. Okay? They say if it's 0, it's a true nonpolar covalent. If the electronegativity difference is 0, that's the only nonpolar. And then everything else is polar. Or some people go, well, from 0 to 0.5 electronegativity difference, that's nonpolar. That's nearly equal sharing. Okay? And then from 0.5 to 1.9, that is polar covalent. And then anything over 1.9, that's got to be ionic. No. No, 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 no. Okay? What you do with an increase in electronegativity is you tend to increase ionic character of a bond. The more ion-like it will become. Okay? But this is not a perfect example of this, because electronegativity is not real. It's a calculated value. It's a theoretical value that was assigned. And the values of electronegativity change depending upon which scale you use. The book uses the normal Pauling scale, but there's a modified Pauling scale and all sorts of stuff, where in the normal Pauling scale, fluorine has a value of 4.0. You ever notice there were no units to that? Because it's not real. Okay? Remember, there's a periodic trend. We discussed the periodic trend that electronegativity increases as you go across a family and decreases as you go down, increases as you go across a period and decreases as you go down a family, okay? With fluorine being the most electronegative atom. Now, take a look here. Fluorine and hydrogen. What's the electronegativity difference between fluorine and hydrogen? 4.0 minus 2.1 gives you the 1.9. Hey, didn't they say at 1.9 it becomes ionic? Right? That's generally where they put that cutoff point. So that means that if I have beryllium fluoride, that's 4.0 minus 1.5. That should definitely be ionic, right? No. Beryllium fluoride is in fact a covalent compound. Polar covalent, but it is a covalent compound. That's why those exact numbers are crap. It doesn't mean anything. Okay? You increase an ionic character. Does it have a significant ionic character? Yes, it does. It has significant ionic character. But it is, in fact, a covalent compound based on our definitions. Okay? What's the takeaway? The takeaway is you increase ionic character the farther away you are from each other. So if you get really far away, like fluorine to francium, that's got to almost be definitely an ionic compound. In general, we say that metals to nonmetals give us an ionic compound because metals tend to have smaller electronegativity values. Nonmetals tend to have higher electronegativity values. But when we're dealing with molecules, something like phosphorus to oxygen, they're fairly close to each other. Okay? They're going to have less ionic character. They're not going to be an ionic bond, but they're probably going to be a little bit more polar. Okay? But things that are right next to each other, like nitrogen to oxygen, that's going to be more nonpolar. With the gigantic exception being carbon to hydrogen, because hydrogen's off to one side. Okay? Carbon to hydrogen is a nonpolar covalent bond.
Especially in those like alkanes.
Right. Well, in any form, carbon to hydrogen, nonpolar. Now, what you're talking about in alkanes, okay, or you're talking about molecular polarity. This is bond polarity. There's a difference. Okay? Questions, comments, verbal abuse? Yeah.
I understand that Krypton, we were able to make lots of them, but
Right.
they could be they-
Why are their electronegativity values so high?
Yeah. I mean, I understand that it technically doesn't really mean anything, but if we were going to put numbers to them, I would have at least put them a little bit lower.
It's a calculated value. It's calculated. So those are actually the results of calculation. Now, why are they so relatively high? Well, look, it does fit into our trend, doesn't it? Okay. Now, the thing is, it comes from that other bit of theory that I had talked about, hard, soft, acid-base theory. It's my guess that the reason that they have such high electronegativity values has to do with how they interact. Okay? That's my guess. But I don't know. Nor, in all honesty, do I really care. Because the research dealing with this is so specialized. Okay? That it's not something that I'm going to run across in daily life. Now, let's say they come up with neon and then they calculate neon to be like 5.12. Okay, then I might actually want to get into it. But yeah, like I said, it's really specialized stuff. So I don't worry about it.
Because they blocked off majority of the livable gases.
Well, that's because those two haven't been reacted. And then part of the calculation with this, the only thing we've done with argon is that compound, HARF, which probably makes it harder to calculate because it's not two atoms, like with xenon, it's xenon tetrafluoride, just 2 atoms. This is 3 atoms, might be a little bit more difficult. That's my guess. Okay? Questions, comments, verbal abuse? All right, remember.